let us start with this problem, which is based on a fundamental concept of neutrons in a gravitational field. Let me explain the concept to you, and that is how they have explained in the paragraph also. The question is somewhat like this. In the familiar classical world, an elastic bouncing ball on the Earth's surface is an ideal example of perpetual motion. So there is a lot of discussion on this thing, perpetual motion. Now what happens? The ball is trapped and it cannot go below the surface or above its turning point. Obviously, above its turning point nahi ja sakta, and below the surface it can't go. All the collisions are elastic. It will remain bounded in this state, turning down and bouncing up once and again forever. Only air drag or inelastic bounces could stop the process and will be ignored in the following. Now, a group of physicists from Institute Loy Langevin in Grenoble reported in 2002 experimental evidence on the behavior of neutrons in the gravitational field of Earth. Now, what they have experienced, let's see. Neutrons in the
class వింటున్నాను
neutrons in the gravitational field of Earth. In the experiment, neutrons are moving to the right. Now just look into this figure and try to connect with the data which is given in the problem. So what they have experienced is that neutrons moving to the right were allowed to fall towards a horizontal crystal surface that is given, and that was acting as a neutron mirror. And where they bounced back elastically up to the initial height once again. This is standard experiment. Gravity is present. Neutrons are being sent in between. Now we have to analyze the problem. Up to this stage, it is fine. So let me just remove this thing and just focus on the requirements of the problem. Now let us focus on the calculative aspect of the problem. So read it carefully. The setup of the experiment is given in the figure. There is an opening, mirror, a neutron absorber is there also, which is at a height of Z. Z is this height, which is capital H. So there is a neutron absorber. The length of the setup is given, which is L. And there is a neutron detector also on this side. So this diagram is fine. It will work. Now all the electrons, neutrons that reach the surface of A are absorbed. जो ऊपर वाले surface से hit कर रहे हैं, they will get absorbed. And they disappear from the experiment. But those that reach the surface of M are reflected elastically. And the detector counts the transmission rate, NH. That is the total number of neutrons that reach D per unit time. जितना वहां पहुंच रहे हैं, total number of neutrons that reach D per unit time. Now comes the first problem. If the neutrons enter the cavity with a wide range of positive and negative vertical velocities, once in the cavity, they fly between the mirror below and the absorber above. That's fine. Now comes the first question, the first part. Compute classically the range of vertical velocities of the neutrons that entering a height Z can arrive at the detector. And assume that L is much larger than any other length in the problem. So to focus on this question with this data which is given on the board. There's a neutron absorber which is at a height of capital H. This is an actual experiment which has been conducted by physicists, and through this experimentation and some usage of quantum physics, so I'll use those equations which we can solve by the basic ideas of modern physics. We are trying to comment on the perpetual motion machine. That is what they are trying to do. So the first question here is that if neutrons are entering from all the places, then from a given Z, the people who will enter, what is the range of their vertical velocity? Gravity in this problem is present. So G is there. So vertical velocity such that the neutrons that are entering from this place should be arriving at the detector D. जो यहां से एंटर करे वो डिटेक्टर तक पहुंच जाए, that's what they want. So if we look at the first part of the question, the only condition that I have got, the only condition that I have got for people at this point is at any cost, their energy at that Z, that is, they have got a mgz term and they have got a half m vz square term. They should not hit the upper surface. So that should be less than equal to mgh. You know, whatever vz I have got, x doesn't have any significance in this problem. That will be maintained. So if I only look into the z part of the problem, so this m will be taken care of. So I'm having vz square is less than equal to, it is less than equal to gh minus z twice. This is coming. So I was convinced it is minus root of 2gh minus z less than equal to vz less than equal to root of 2gh minus z. We will gradually build the problem. So first part was straightforward. So in a multi-correct, first question was this. ये तो पता चल गया. So irrespective of L, people who are having this Vz will definitely reach that place. Because whatever they keep on doing up and down, they will not be absorbed by the upper surface. So they will reach that point. This much is fine. आगे चलें. Now let us talk about the B part of the problem. Let's see what he wants here. So read this carefully now. Now his question is, in the second part, read second part, he says, calculate classically the minimum length of the cavity LC, L limiting length of the cavity, to ensure that all the neutrons outside the previous velocity range, regardless of Z, are absorbed by A. And your Vx is there with you, 10, and your H is also there with you, which is 50 microns. Vx is 10 meter per second, and your H is 50 micron. देखो तो खुद ही कह रहे हैं that this time he was very clear that he wants you to calculate the minimum length to ensure that all the neutrons who are not in that velocity range are absorbed by A. But those who are in the velocity range will obviously be absorbed by A, irrespective of the length. So obviously this question does not have any significance for those people. But definitely for those who are outside the range, for them, I need to have some condition on L, and that's why we are searching for LC, which is the minimum value of the cavity. इतना तो कम से कम होना चाहिए. Just give it a good thought that if I am calculating the minimum length of the cavity, what should be the striking condition I should be using while solving this problem? So now, what I think is, correct, correct. That means what you are trying to say is, while you are calculating for LC, I'm just trying to draw the diagram for LC. Let me observe a person, just focus on every condition. Let me observe that neutron, which is just entering from the point Z is equal to H. The person who is entering from this place only. And that also a person whose velocity in the Z direction is 0. I'll explain everything. Just focus on this. Why I'm taking this, that is more important. If I take that person which is at the highest point, and this guy who is having his Vz to be equal to 0. If I talk about this person, he will also have some Vx because Vx is given here. He will have some Vx. So now, if I want him to be absorbed, what I want is he will go down under gravity and he will come up. And by the time he is about to hit the surface, let it just get absorbed. If this happens, that means my Lx comes out as Vx into time of flight. And time of flight now for this guy comes out as twice of the time. So it is actually root of 2h upon g. And that means answer for LC should be equal to Vx into 2 times root of 2h upon g. Think about the condition, why we have written this. I am getting 2 Vx into root of 2h by g again. Let's see. Now remember, all those people, anybody who will have any velocity in the upward direction will obviously be absorbed. So I am not interested. Anybody who will have any velocity in the downward direction will also get absorbed because by symmetry, when it will come up, it will have that vertical velocity. So for the limiting case, I am observing only for a person who has got a 0 velocity. And when he said minimum length, I mean, this is the least that you require. For any other person, I mean, you don't need that much of length, na? You're getting a point, na? For people who are not falling from this point, so somebody can say that while I am calculating LC, I am discussing that particle which is at the highest point. He is the critical person, na? If I can ensure that he reaches the absorber here, then definitely those people will definitely reach there. But I am only discussing those people who are outside the spectrum. Those who are inside the spectrum are already reaching for any value of L. Those who are outside the spectrum means they definitely have a tendency to hit the surface. From whichever Z you leave them, they have a tendency to hit the surface. So the only thing is, you have to ensure that by the time they are about to hit the surface, before that they hit the absorber. That's what I'm trying to do. And to solve for that condition, I'm ensuring that I am able to manage the highest particle. Even in that state, when he doesn't have anything in the vertically down, upward ka to koi matlab hi nahi hai. He doesn't have anything in the downward direction. Because if he does have something, obviously his time will further reduce. You got the point, no? So when he was very clear, he said, calculate classically the minimum length of the cavity to ensure that all neutrons outside the previous velocity range, regardless of Z, are absorbed by the absorber. Now comes the more complicated spectrum-based question. So now the third part of the question is more different, rather, I will say. Now read it carefully. There is some calculation involved. अब कहता है the neutron transmission rate n as a function of h, we want to measure it at d. Indirectly, what he wants to do, whosoever is entering from this side, who is capable to cross this barrier, he wants to count those numbers. Only they can be counted because they will reach only, right? So now I want to find out the classical rate, which rate we are discussing, NC as a function of h. That's what we are interested in. Assuming the neutrons arrive at the cavity, now you have to be careful. With a vertical velocity Vz, अब जो enter कर रहे हैं उनके बारे में बात हो रही है, Vz and at a height z, being all the values of Vz and z equally probable. So probability distribution is fine. Now what and how are we going to solve it? So he says, give the answer in terms of rho. Now rho is important term for me in this problem. What is rho? The constant number of neutrons per unit time, per unit vertical velocity, per unit height that enter the cavity with vertical velocity Vz at a height of z. Now tell me, how can I find out the transmission, the classical rate NCH? मतलब वो total height अगर h है तो NC term लिखना है. So I am interested in NC in terms of that gap h in the third part of the problem. Obviously, in this problem, we are talking about the quantum states of neutron as they appear in the gravitational field of Earth. Right? So let us try to write. So do one thing. While solving for this part, let me talk about a gap which is capital H. Let's say z is equal to 0, z is equal to capital H. I am discussing this problem for a z over a dz. Now try to understand that all those people who are entering from this dz, who are capable to reach, they lie in a spectrum where we have the spectrum which we have written in first part of the question, from a minus value to a plus value. So what we want to say now, we want to say that dnc by dz should be equal to rho. अब रो डिफाइन ही उसने अलग तरीके से किया है. So what I will do here is I will take V max that I would have written as Z minus V min that I would have written at Z. Basically what we are trying to say here is this expression should be rho multiplied by this gap which we have discussed in the previous problem. It is 2 root 2g h minus z. It is 2 root 2g multiplied by h minus z. Remember, when you have been given rho, they are talking about per unit time neutrons, that's fine. Per unit vertical velocity, per unit height में dz ले लिया. And this per unit vertical velocity को cover करने के लिए I have written this. Because all the vertical velocities which we have got is over that spectrum of 2 into root of 2g h minus z. So per unit spectrum है ना, per unit vertical velocity का मतलब per unit spectrum size है. So this is the spectrum size. So I think dnc by dz का value 2 rho root of 2g h minus z is what we will get. So if I want to write total number of people now, so I think this should work out that it should be integral of 2 rho root of 2g h minus z dz, h minus z dz from z is equal to 0 to z is equal to h. These many number of people, and this should be the value of nc as a function of h. Integrate it out and check the final expression. should be a normal thing to integrate this. This finally I have got the result with me. So when I solve this, this answer comes out as 4 rho by 3. You people can check times root 2g, root 2g, and capital H raised to the power 3 by 2 I have kept separate. H root H I O. So 4 rho by 3 root of 2g into capital H raised to the power 3 by 2. This is the function that he is expecting in third. These are the number of people. So for a width capital H, you can expect these people to reach. So, I mean, basically these were the people who were having the capacity to reach. I have integrated. Properly they have defined rho, I have used. Now comes the better thing. Now we are going to quantize the problem. Now let us go to the fourth segment of the problem where we will do some quantization. So let's see what we want to write here now. So read this point and then you have to answer appropriately in continuation. Don't worry about this question part. I'll explain this to you. Just go through the condition. The experimental results. Now what happened? Up to this much, things were fine. The experimental results which were obtained by the group, Grenoble group, disagree with the above classical predictions because there is all the results that we have written are like continuous spectrum. And now they are saying that there should be discreteness because practically this is not possible. So what they observed was, showing instead that the value of NH experiences sharp increases whenever H is crossing a particular value. So N जो था वो sudden discreteness feel करता है for given distinct H values, which is given in the sketch. In other words, this is experimentally observed. In other words, the experiment showed that the vertical motion of neutrons bouncing on the mirror should be quantized. And in the language of Bohr and Sommerfeld, used to obtain the energy levels of hydrogen, this can be written as the action of S of these neutrons along the vertical direction is an integral multiple of the Planck action constant H. उसने वो भी दे दिए. So now the question is, if you define S as integral Pz z dz for different values of n by the quantization rule, Pz is a vertical component of the classical momentum, and integral covers the whole bouncing cycle. You have to be careful. While you will write this expression, it covers the whole bouncing cycle. Only neutrons with these values of S are allowed in the cavity. We'll calculate those S. And using this, his question is very clear. If you read the question carefully, he says, compute the, just read it. I mean, what he demands here is, what is the turning height Hn and energy levels En associated to the vertical motion, and using the Bohr-Sommerfeld quantization, what is the numerical value of H1 in microns and E1 in electron volts? So I'll just paste it here also for you so that you people can solve it now. Lot of information is provided. Just find out the turning heights, and I need the minimum, I mean the least value also he has said. Can you find out H1 in microns and E1 in electron volt? They have used this condition that S is equal to integral Pz as function of Z dz, and that is equal to NH on 2 pi, N is equal to 1, 2, and so on. That was given or mentioned in the problem. If you wish, you can just go through the main information again. So when you cross some specific H, there's a sharp increase in NH. In other words, what is happening? That vertical motion of neutrons bouncing on the mirror is quantized. तो अगर action S of these neutrons along the vertical direction is integral multiple of the Planck action constant H और S को ऐसे define कर रहे हैं हम, N are having natural positive integral values and Pz is the vertical component of the classical momentum and integral covers the whole bouncing cycle. Now, what we are interested in is the basic expression of, we are interested in the expression of Hn and En respectively in this problem. So obviously उसकी least value तो निकल ही जाएगी. That's not a big hassle in the problem. So let me define S. S क्या लिखा था उसने? तो यहीं से start करते हैं. S is integral Pz z function dz. That's what we have to find out. I'll substitute the values and put appropriate limits. Don't worry. So now, what I should be doing? 0 से h का twice कर लेते हैं, तो complete cycle है. So take twice and integrate it from z is equal to 0 to z is equal to h, and take mass term also m for the neutrons. और v का function अब ले लो. क्या मिल रहा है आपको? The term that you need here, you should substitute. So 2 term is there, m term is fine. Then what is the final term we are getting in this problem? वहां हमें velocities मिले थे from minus 2g h minus z. So basically, seems like that spectrum of momentum is, what was the value of the function? Function बताओ एक बार. So I think we have written earlier, it should be root of 2g. It is root of 2g h minus z twice of that and multiply this by dz. Just look into this case. So 2, 0 to h is just because of the bouncing cycle. Pz, dz term was required. That we have written like this. What does this integral convert itself into? Does it come out as 4m by 3 root of 2g, the similar expression which I have written previously, into capital H raised to the power 3 by 2? Fine. I'm not missing any constant there. Na? Your result is coming out as, so what I have done, I have taken 2 times z is equal to 0 to z is equal to h. What is the velocity spectrum? That is root of, actually this is something that I have taken twice. Na? मतलब अगर मैंने वो cycle ले ली है तो मुझे momentum नहीं लेना चाहिए. If I have taken the momentum already, then there is no point taking it twice. Just check. This much comes, that's fine. And once we are able to write our S properly, then everything is fine, because he has already said that this term, he has said that this should be equal to n into h. N into h. So what he was trying to do in this problem, when he said find Hn, for me, Hn in this problem was, n h into 3 upon 4 capital M root 2g, this whole raised to the power 2 by 3. It was proportional to n raised to the power 2 by 3. Rest, obviously, the constants are also required, but I will get my expression of Hn. And if we are done with this, then as far as En is concerned, that should be mg into Hn. mg So this expression and En, both of them can be calculated. After that, when he says find out the value of H1 and E1, that is purely calculation. All the things have been given. You can calculate it. I'm not doing the calculation. Given the data, you can find it. Now leave that part. Let's come to the final part of this problem, which is again conceptual. This is fine. This much is fine. Now he says, read this again. Again, he says the uniform initial distribution row of neutrons at the entrance changes during the flight through a long cavity into step-like distribution, which is detected at D. And from now on, we consider for simplicity the case of a long cavity with H less than H2. Classically, all the neutrons with energies in the range considered in question were allowed through it, while quantum mechanically only neutrons in the energy level even are permitted. This is the same even which we have calculated in the previous part, the least possible value. So I'll use it while solving the last part. And according to time, energy, Heisenberg, uncertainty. Now he introduces uncertainty principle. This reshuffling requires a minimum time of flight. Simple बात बोल रहे हैं. The uncertainty of the vertical motion energy will be significant if the cavity length is small. How come? Because that is where the question is. This much is not required actually, but we can directly think over this. क्योंकि वो कह तो यही रहा है, this phenomena will give rise to the widening of the energy levels. Now, from the exam perspective, I don't think he will explain this part, but he can directly put up this question that estimate the minimum time of flight TQ, right? And the minimum length LQ of the cavity needed to observe, just focus on the question, to observe the first sharp increase in the number of neutrons at detector. That behavior which we have observed, if you want to observe the first sharp increase in the number of neutrons at the absorber, what do you think about the minimum time of flight and what is the minimum length of the cavity needed? These are the two things he is putting up. Use Heisenberg's uncertainty principle. Now, delta T and delta E, that should be greater than equal to H cut term and indirectly for this problem, uska bhi minima le lo. So maybe I will write delta X, delta T greater than equal to H bar term. And remember, these are for all possible values. So think in terms of their minimum possible value, both of them. If that satisfies this, then obviously it is satisfied. Now you have to think about delta X and delta T term. Now delta X will be only because of delta T, because delta X seems like Vx into delta T. So maybe I'll separately write that delta X is logically Vx into delta T, and that should be greater than equal to, delta X is greater than equal to what? Delta T के बारे में तो पता ही है, H upon delta E. So that term becomes what? Vx H bar term by delta E. Just observe this carefully. Delta X should be greater than equal to Vx term into, wait, this is separately I have written for the length. So forget this term. Delta T was H bar delta X. Now what we are trying to write here is just we are trying to substitute our delta T term. That's what I have done. Now it seems that calculation should be fine because already I needed some to think like this. I could have written it like delta, Actually, I wanted to look into the proportionality. Ab theek hai. So I can write delta E into delta T term that is greater than or equal to h bar, and then I can substitute. Fine. एक ही चीज. So delta x delta T that is greater than or equal to h bar term. That is fine. Delta T delta E. Then delta x I knew that is Vx into delta T, and that should be greater than or equal to Vx, and delta T is greater than or equal to h bar upon delta T. Now tell me what is the minimum time TQ and the minimum corresponding length. So I think it should be simply h bar cut term upon E1, क्योंकि delta E की तो जो पहली possible value है, that is E1 only. So h upon E1 term, I mean, ये least critical value दिख रही है मुझे. The minimum time of flight seems to be this. So it is, this can be calculated because already I have calculated E1 in the problem. आ जाएगा TQ term. And the corresponding minimum length that you want, I think again, you can calculate Vx into this. So it should be Vx into h bar term divided by E1, the minimum gap there, energy gap, delta E that we are discussing. But as such, that size is the highest, but the first order jump ki baat kar raha hu. So technically what he is trying to say in this combination is that T and E terms की जो uncertainty है, उसमें एक order पता चल गया minimum का, और E की uncertainty can be correlated with the different possible energy levels. And in a critical combination, that uncertainty I have connected with E1. And T is fine, that I can relate with the uncertainty in the length with Vx. Rest everything is fit and fine. Connect the inequality properly and you will get your result. Right, so let me take up the second combination for the day. Now this second problem is based on a slinky spring combination. So you have to be careful as you go through the question. You need to first go through the data that he has provided, and then we will solve this, what he is trying to say in the problem. It is a zero length spring and the slinky coils. So let's see how he defined this. He has defined everything. So he has said that, I'll just increase the size of this so that you people can first read it, then I will focus on the question. एक बार data पढ़ लो बेटा आप लोग. What he is trying to do. So this problem he said that he has defined a zero effective length spring ZLS. Now ZLS is a spring for which the force is proportional to the spring's length, right? That is simply बोल रहा है कि F is equal to KL for L greater than L0. And L0 is the minimum length of the spring as well as its unstretched length. And while you are in this category, the force is not going to act. The spring force will be zero. And as you cross this L0, it will follow a linear relation. So this is the behavior of the graph like this. That's what is the behavior. Up to L0, this is the behavior. And the slope of this line is obviously the spring constant. Okay, all fine. Now, ZLS is useful in seismography and allows very accurate measurement of changes in the gravitational acceleration. Here we shall consider a homogeneous ZLS. Forget this. Up यहाँ important है. This homogeneous ZLS whose weight capital Mg exceeds KL now. That is what he is considering in the problem. And we define the corresponding ratio. एक term is to define K alpha. Alpha is KL naught upon Mg, and that value is actually less than 1. And this he has done to characterize the relative softness of the spring. He will, I mean, all the questions when we will solve, we'll calculate everything, so don't worry. So this toy, which is known as slinky, may be such as a ZLS. So just work we'll work on a ZLS in this problem, right? Data is fine with you? Just note this L naught, K, F is equal to KL, all these characters, and alpha. Remember, alpha is KL naught upon mg. It is given to be less than 1. So mg is greater than KL naught. Once you are clear with this information, let us work on the first part of the question. कहता है consider a segment delta L of the unstretched ZLS spring, which is then stretched by a force F under weightless conditions. What is the length delta Y of this segment as a function of F, delta L, and the parameters of the spring? F, delta L, and the parameters of the spring. That is the first part of the problem. There is some force F which you are exerting, right? So this will try to change the length from L0 to some new length L. And I am assuming that every part of the spring is behaving uniformly. Remember, that is the beautiful thing in this problem. First, he has taken weightless conditions, where every segment has got a uniform behavior. And in the second part of the problem, that uniformity is being inculcated because of gravity. So the lower part of the slinky spring will behave differently from the upper part. But abhi uniformity hai. So what should we say? बराबर बराबर distribute कर लेते हैं. So what is the delta Y you want to write? Like if you take any before you solve, if you take one thing is fine. If you take delta L segment of the spring, obviously spring constant is inversely proportional to the length. So I could have directly said that if you give me natural length L0, he has given the natural length of the spring is L0, because minimal length wali baat bhi boli and stretch length is also said. So I should have said that K into L0 is the K of this part, K prime, into delta L, inverse proportionality. So K prime of that delta L length is K L0 upon delta L. That is fine. So if you give me a segment delta L, I know that this is the spring constant of that segment. So if you are trying to apply some, force F, so it seems like that F upon K prime, that is K L0 by delta L. So F delta L by K L0. And remember, this is the extension of that part. And I am again presuming that extension is large in comparison to its natural length. So that I am treating as DL type of thing. Or ye term, F by KL0 is some order higher than delta L. This is a central assumption in this problem. ताकि जो उसका extension है वही उसकी final length. This is what I have taken, he has taken while framing the problem. So this comes up, तो उसकी length इतना हो गया. So answer to this problem could be like F delta L upon K L0 term. लिख सकते हैं? But there is one concern. We are writing F delta L upon K L0. है ना? And initial length was delta L only. ये final length लिखी है. So it should be this or this. Rather, I should say the greater of this. So answer से यही दिया है. The max of these two values should be the result. Because there is a possibility that delta L doesn't stretch. The force is such that we fall into this category. So you got this point. So if it stretches, then it's fine. If it doesn't, then answer is delta L. So if this value is less than delta L, then delta L is the answer. Otherwise, this is the answer. So max of this and this. This much is fine. Now, Just focus on this because I'll go to the second part of the problem. Now, what does the problem say? So let me just focus on the A2 part. I mean, you can go through the question and just focus on this second part of the problem A2. This seems simple to me because here he is saying for a segment delta L, what is the work delta W required to stretch it from the original length delta L to a length delta Y? उसकी लेंथ को डेल्टा एल से डेल्टा वाई ले जाएं तो व्हाट इज द अमाउंट ऑफ वर्क दैट यू विल डू इन दिस पार्ट so seems like delta L to delta Y is what you want to move like तो ऐसा लग रहा है जैसे K L naught by delta L the spring constant so this term here is delta L ये तो हो गया उसका spring constant and if I am at extension x kx dx the integral of this expression should work. And you are moving from x, which x values? So from delta L to delta Y, I am taking x from delta L to x is equal to delta Y. So seems like this result is k L naught by delta L 2 and a factor of delta Y square minus delta L square. When he says that you will stretch it from delta L to delta Y, this will be the obvious result. Obviously, this time we are talking about, otherwise work is not required if force is 0. So I am obviously in the second segment. So that was central to this problem. Now the next two segments are actually the more interesting part of this question. So he says throughout this question will denote, now you start it afresh. Now what I will do, I will suspend this spring. I'll denote a point on the spring by its distance from the lower side. You take that small l, और अभी gravity नहीं था, तो small l was lying between 0 and L naught. The question is from the bottom of the spring where it is unstretched. In particular, for every point on the spring, L remains unchanged as the spring stretches. मतलब समझ गए ना? So actually in lab you won't see that L, but you have marked some L's with respect to the previous situation. So he is just formulating the problem for you. Now comes the problem. Suppose you hang this spring by the top end so that it stretches under its own weight. Now, can you tell me the total length of the suspended spring in equilibrium? And I need this answer in terms of capital L naught and alpha. What was alpha in the problem previously? Alpha was K capital L naught upon capital. So alpha is a constant which he has defined as this term previously in the question. And he was very clear that alpha is less than 1. This is all given to you, so don't worry about this. Think about the length of the spring in terms of L naught and alpha in this problem. So try to write that expression. Now, while solving this, question, what I will do, first I will try to find out a segment of the spring, this suspended spring here, and this is non-uniform, so just I have explained it like this. Maybe first I will try to find out a person at some distance small L naught from the bottom which doesn't even stretch. So that is the first thing. Let us try to find out that L naught. And for that, the thing is the weight of this segment, L naught segment. So I would have written if the total mass is capital M and the total length was capital L naught. So capital mg upon capital L naught into small L naught. This term is there. And that should be equated with that force which was previously given, which was K capital L naught. He was very clear that till the tension is K capital L naught, it won't stretch. So I've just written that term here. And that helps me calculating small L naught. So small L naught for me is K capital L naught square upon capital Mg. Capital L naught is the total natural length. और इसमें एक टर्म अल्फा आ जाएगा because K capital L naught upon capital Mg. So this becomes alpha capital L naught. Keep this term with you. Now comes the more appropriate section of the problem. So now what I will do, I'll take some segment for a L which is greater than L naught. Let's see what happens. और वहां जा जाके extension निकालने की कोशिश करें, right? So try to go to a general L and try to find out the extension. So try to go to a general L which is greater than L naught from bottom, and you understand that K there becomes what? What is that? K L naught upon DL. So I'll go to a L, I'll cut a DL, and I'll get my spring constant, which becomes K L naught upon DL. Right? And if I divide this weight up to that L, which is capital Mg upon capital L naught into L, check that. Capital Mg upon capital L naught into small l divided by K capital L naught upon DL, that will give me the stretch there. Just find out this value. क्या निकल के आता है? Solve it. It comes out as, if I solve this, this comes out as capital Mg upon K capital L naught square small l dl. Check this. Fine. अब इसको अल्फा के टर्म्स में कन्वर्ट कर लेते हैं. तो मेरे ख्याल से ये स्मॉल एल डी एल डिवाइडेड बाय एल नॉट ही आ गया. दिस स्मॉल एल नॉट हियर was K capital L naught square upon mg. This is what I'm going to get. And if I can integrate this term properly, so I mean, what I think is I can integrate this small l dl upon L naught from small l is equal to L naught. So small l is equal to capital L. Small l is equal to L naught to capital L. So that becomes what, like 1 upon L naught to bahar ho gaya, by 2 aa gaya. It is capital L naught square minus small L naught square. So now I'll have capital L naught square upon 2 L naught minus L naught by 2. Remember, this is actually the stretch, but I have assumed that stretch is large in comparison to the DL length. So when he says, I'll just focus on the question again. When he says all this given, what is the total length? So the expression for capital H that I will write here will be niche wala small L naught. So small L naught plus the extension which you have got. So capital L naught square by 2 L naught minus L naught by 2. So this becomes L naught by 2 plus capital L naught square upon 2 L naught. That will be the result. That is what it is. It is small L naught by 2 plus capital L naught square upon 2 L naught. And if you just try to write it in terms of alpha, this expression, just check, rewrite this in terms of alpha. So this is capital L naught by 2 times alpha plus 1 upon alpha. Check that. Small L naught and capital L naught, I think we have written that relation because small L naught was alpha into capital L naught. So just use this equation on this page and small L naught ko maine eliminate kar liya. So I got my result. So my result is alpha into capital L naught by 2 plus capital L naught by twice of alpha. This much is fine. Now comes the most appropriate, even more appropriate part of this question. Extension निकाल लिया इसने, length निकलवा ली. Now he says in the question, go through this data. I mean, the problem is that he will leave this spring from the top. I think on the previous page only, that question should be there somewhere. After this, I wanted to introduce the dynamics of the problem. I think the dynamics, oh, somewhere he has missed the page somewhere. Okay, no issue. What I will do, let me explain the statement. From this point you can read, but I'll explain what he is trying to do in the last part of the problem. So he says experiments show that when the spring is hung at rest and then released, ceiling se tang do aur chhod do, now what happens? And that is what he has tried to explain. It gradually contracts from the top, gradually contracts from the top, while the lower part remains stationary. This is what happens. This you must have observed also. अगर ऊपर से छोड़ देंगे तो ऊपर वाला दबने लगता है और नीचे वाला लगता है जैसे वो स्टेशनरी है. The lower part remains stationary. As time advances, the contracting part moves as a solid chunk, and that's what he has tried to show here. The contracting part is moving like a solid chunk, right? And accumulates additional turns of the spring while the stationary part becomes shorter. The stationary part is becoming shorter throughout, if you see. So the point is, every point on the spring begins to move only when the moving part reaches it. अगर स्प्रिंग के नीचे से देखें तो ऊपर से चलता हुआ हिस्सा जब उस पार्ट तक पहुंचता है तभी वो पार्ट चलता है. And that is what everything he has tried to depict here. So the bottom end of the spring, now you can read in continuation, the bottom end of the spring starts to move only when the spring is fully collapsed. तो जब ऊपर से पूरा collapse हो जाएगा, then only this head will move. And fully collapsed and reaches its unstretched length L0. So जब ऊपर से गिरता हुआ spring पूरा collapse होके अपनी natural length L0 पे आ जाएगा, then only the lower part will move. So he has specified everything, which is actually the right behavior also, which happens. And now the questions will come up. So after that, the contracted spring continues falling straight downwards without tumbling as a rigid body under the influence of gravity. So here he has given a lot of things. A sequence of pictures taken during the free fall of a slinky, part 1, and the stationary part 2 during the free fall of the spring. Now, there are more questions, but I am only interested in this last one. In the remaining parts of the question, you are asked to base your solution on this described model. You may neglect air resistance, but you are not allowed to neglect L0. Capital L0 को रखना. The question was, what is the time it takes from the moment the spring is left to fully collapse? That means attain a length of capital L. So because of the weight, एक extended spring को अगर हम छोड़ दें, so from that situation, how much time will it take to collapse back to the minimum length L0? And you have to express your answer in terms of L0, G, and alpha. So there is some calculation of time which is required. I'll give you the basic idea and that you can pursue the problem. Actually, it's a wonderful problem based on center of mass. The idea to the problem is that once you leave it from the top, at that very instance, if somebody can find out the location of center of mass, and when it will fully collapse, at that time the location of center of mass is L0 by 2. So अगर मुझे ये पता चल जाए that with respect to the base, it is where it is, HCM, at t is equal to 0, and then the center of mass will come at L0 by 2, then the displacement of center of mass is actually half g t c square. And this is the first equation. This will give me the answer. Now the problem is how to calculate the HCM value. So HCM minus L naught by 2 is half GT square. HCM is to be calculated. Now, what are the terms you have to write? So I'll write one integral, then you will further solve it. So what I should do, while writing HCM, let's say this is the state while I am writing HCM. So I should have written the total mass 1 upon m. In the box, I should take sigma over I, mi by I. तो जो नीचे वाला लेंथ है वो L naught by 2 है, तो उसका तो लेंथ हो गया. That guy will have L naught by 2 and his mass is alpha times the total mass. Because alpha is, you got it now? This length is small L naught, but center of mass is L naught by 2 for that person. And his mass is alpha times the total mass. Alpha is L naught by capital. Good enough for first part. And the second term is to be written as an integral for the remaining parts. So what I will do, I'll write this integral from L naught to capital L naught. I'll write a dm term. I'll write a h term, whatever it is, h. H as a function of L. H as a function of L, I'll write, and then I'll try to integrate it from L is equal to L naught to L is equal to capital L. Now, two things are required. dm is simple. dm is simple. dm is capital M upon capital L naught into d small m. So no issues with that. Now, only thing, rest is calculation. Only thing is I need all of you to write this value of HL. अब HL आपको लिखना है. And that we have calculated earlier. वो आया था L square by 2L naught. Just use it. Small L square by 2L naught plus L naught by 2, I suppose. That was it? Yes. Small L square by, this is fine. Small L square by 2L naught plus L naught by 2. You remember this term, no? I've written this earlier. Now it is calculation, you'll get your answer. So, this calculation you can do, and if you go through the previous page, you'll get the term that I have written. I will have to stop the class here, and I expect all of you to solve the remaining part in the question. Take care of yourself, and I'll catch up with you tomorrow with some more problems for top level JEE advanced. Good night.